Okay. Good afternoon. Today our topic is curves and super elevation. Okay. So, curves. Actually, curves are introduced on railway track to bypass obstacles, to provide longer and easily traversed gradients, and to pass a railway line through obligatory or desirable locations. Normally, horizontal curves are provided when a change in the direction of the track is required, and vertical curves are provided at points where two gradients meet or where a gradient meets level ground to provide comfortable ride on a horizontal curve. The level of the outer rail is raised above the level of the inner rail, and this phenomena is known as the super elevation. So normally, in geometric design study for railway, there are lots of things which are involved with geometric design. Like earlier class, in the earlier class, we have seen the gradients. After the gradients, we have these curves, super elevation, and lots of things which are normally exist in geometric design. In our railway engineering, as you just heard, the curves are introduced on railway track to bypass obstacles. If we go ahead with curves, so there is first that the things that is circular curves, and circular curves the is involved with some parameters, some elements, and methods of setting out circular curves. So in parameters of circular curves, first there is radius of degree of a curve. Normally a curve is defined either by its radius or by its degree. Radius or degree, these two things are important to define a curve for our highway engineering also, and in railway engineering obviously we define the curves by these two values, radius and degree of curve. And the degree of a curve denoted by D, capital D, is the angle subtended at center by a, suppose, 30.5 meter arc. Arc is the part of the circle, and this arc is subtended by its center. So if that is the condition, the angle subtended at its center by a 30.5 meter arc, therefore the value of the degree of the curve can be determined as from this circumference of a circle. Suppose it's a equation of our circumference for a circle, that is 2 pi r, and angle subtended at the center by a circle with this circumference, that is 360 degree. So 360 degree, normally as we know, the subtended angle for a circle, that is 360 degree, and which is actually one dot at the center point of the circle, this 360 degree, and angle subtended at the center by 30.5 arc or degree of curve should be 360 degree by 2 pi r that is our circumference, into that angle 30 that the arc length 30.5. So 360 degree by 2 pi r into 30.5, the given value of the r 30.5, this is 1750 by r. This is the angle subtended at center by a 30.5 arc. So any arc length, if I have any arc length of a circle, then I can easily calculate the subtended angle of that arc. So the formula is or 1750 by r. Easily we can find out, and r value is in meter. Then in case where the radius is very large, the arc of a circle is almost equal to the chord connecting two ends of the arc. Okay, what is chord? We'll see next slide. But in case first you can see the here, or you can see this notation. In case where the radius is very large, the arc of a circle is almost equal to the chord connecting the two ends of the arc. Suppose this from this figure you can see, this is the suppose DAE, one arc. This is one arc of the circle, and D is the chord length. Okay, this is D, this D is the chord of the arc, and DAE is the one of the arc of a circle, and DE is the chord length, which we have discussed. So in case where the radius is very large, the arc of circle is almost equal to the chord connecting two ends of the arc. The degree of the curve is thus given by the formula D equals to 1750 by r. Okay, D equals to 1750. This is the formula to find out the degree of any curve. So if r value is available in meters, we can find out the degree of the curve. Suppose a 2-degree curve therefore has a radius of 875 meter, because the formula is 1750 divided by r. So r value we can find out. Obviously D equals to 1750 by r, so r equals to 1750 by D. If D value also available, we can find out the r value. So D or R we can find out which is available to us. Next, the relationship between radius and versine of a curve. Okay, these things are some things which are actually needed for railway engineering, not for in your highway engineering. Some things are important for railway engineering. Some these descriptions, some derivations, little bit things which are more than your highway engineering. So like relationship between radius and versine, this is actually the mathematical things, but we have to know what is the relation between radius and versine of a curve. So versine is the perpendicular distance of the midpoint of a chord from the arc of a circle. So AB is suppose AB one is the extended length. D is already said, D is the our chord length, and DAE is the arc and the part of the circle DAE. So AB, this AB is the actually versine, extended length from the chord. The relationship between the radius and versine of a curve can be established as shown in figure. Let R be the radius of the curve. R is the radius of the curve. So normally the diameter is the 2r. Okay, if r is the radius of the curve, and suppose circle, if we consider a circle, complete circular circle, then the radius, if radius is r, the diameter should be 2r. From the figure, a relation has been shown where a circular curve is there, and the versine AB, which is connected to the chord from the arc. AB is the versine. So the relationship between the radius and versine of a curve can be established as shown figure. Let R be the radius of the curve, C be the length of the chord, D is the C, actual C be the length of the chord, and V be the versine of a chord of length C. So this C, on this C line or chord line, versine V, versine length AB of length V, AB is the versine of length V of a chord of length C. Length C is length C, that is D. On D, this versine V is present actually. They are mean to say. And AC and D being two chords, AC, this AC, and D, two chords meeting perpendicularly at a common point B, this B. Simple geometry can prove that AB into BC equals to DB into B. Okay, as per geometry, AB into BC equals to DB into B, or V is the versine, that is AB, into 2R minus V, that is the 2R means the diameter minus this versine, that is BC. Okay, the BC is the 2R minus V. So V into 2R minus V equals to actually C, or C by 2 into C by 2, that is DB into B. D is the complete C, and DB is the C by 2, and BE also C by 2. So AB into BC, if AB into BC equals to DB into B, so AB is V, BC is 2R minus V, equals to DB is the C by 2 and B is the C by 2. Or simply you can say 2RV minus V square equals to C square by 4 from the geometric relationship. And from this figure, relation between radius and versine of a curve, V being very small, versine is the very small, so V square can be neglected from this equation. Therefore 2RV equals to C square by 4, or simply V is equals to C square by 8R. In equation, V, C and R in same unit, say meters or centimeters. This general equation can be used to determine versines if the chord and the radius of a curve are known. So chord length and radius of the curve is known, then easily we can calculate the versines or this AB value, the length, extended length from the chord to the arc or part of the circle. Okay, if this is completely perpendicular, suppose AC and D to two chord of the circle, and both each other crossing with perpendicular, and if the value of R, that is radius of the curve for circular curve, actually the radius of the curve is known, and also the chord length of the curve is known, then easily the versine or AB value can be calculated by this equation. V equals to Varsine equals to C. C is the chord length, C square by 8R. R is the radius of the curve. Next, if values in metric units, we need actually normally all the cases for numerical calculation for academic as a academic persons, you are also part of the academics. So in academy we are normally use the metric units. Okay, so for metric units equation can be also written as V by 100 equals to C square by 8R. Here R is the radius of curve, C is the chord length in meters, and V is the Varsine in centimeters. Remember, V is the Varsine in centimeters. If you use this equation V by 100 instead of V equals to C square by 8R, if we use the V by 100 equals to C square by 8R, then R is in the radius of the curve, C is the chord length in meters. Okay, and V is the Varsine in centimeters. Okay, and V equals to should be C square into 100 by 8R, or 12.5 C square R centimeter, or 125 C square by R millimeter. This is the actual formula to find out the length of the Varsine in centimeter or millimeter. For determination of degree of curve in field, okay, determination of degree of a curve in the field, for a chord length of either 11.8 meter, actually normally 11.8 meter is used, length of 11.8 meter is normally adopted for determining the degree of the curve in the field. The relationship between the degree and Varsine of a curve is very simple for these chord lengths as follows: V equals to 12.5 C square by R, and D, the formula which is coming from this equation, D equals to 1750 by R. Okay, D equals to degree of curve equals to 1750 by R, and Varsine is the 12.5 C square, that is chord length square by R, that is in centimeter. So from the two equation given above, the degree of the curve for a 11.8 meter chord can be determined. Suppose instead of R, we can R value we can write 12.5 C square by V, and D equals to, normally D equals to 1750 by R. So instead of R we can write 12.5 C square. So D equals to 1750 V by 12.5 C square. And if we have the chord length like that 11.8 meter, so easily we can put in place of C this value 11.8, or we can calculate the relation between D, degree of curve, and Varsine of curve. Or obviously if I have the value of D or V, if I have to find out the D value, so we need this V value, Varsine value, or if I need to find out the D value, we need the I have to find out the V value, I need the D value to find out Varsine. Also from this equation we can find out, from this equation also find out. And this is the actual relation between degree of curve and Varsine of the curve. Another name of the Varsine is the extended length. Okay, extended length, somewhere it is used. Many places the writer has they have used the extended length instead of Varsine. After this relation, the maximum degree of curve which have been provided by the Indian Railway, the maximum permissible degree of curve on plain track and on turnouts. Suppose in our track, normally our tracks are broad gauge, meter gauge and narrow gauge. So maximum degree for broad gauge is 10 degree, minimum radius is 175 meter for broad gauge for plain track, and this value on turnouts maximum degree is 8, minimum radius is 218 meter. For meter gauge on plain track 16, maximum degree is 16, minimum radius is 109 meter. On turnouts maximum degree is 15 and medium radius is 116. Narrow gauge 40, minimum radius is 44, maximum degree is on turnout 17. These values are needed to actually judge your numerical, because sometimes if you are getting some values which is not acceptable for, suppose you are solving any problem for broad gauge line, or you are getting minimum radius 200, above 200 for plain track, this is not permissible, because you should know these values to correct your numerical problems, to correct your answer for numerical problem. In during exam, when you will get the questions, you have to solve the you have to find out the minimum radius, maximum degree of your car, and after solving you are getting, suppose the maximum degree of curve 15 for plain track for broad gauge line, then it is very odd numbers and the answer is not correct for that cases. So these values are needed to just to remind what should be my value for calculation, what should be my should come the numerical value for my calculation. This is the some examples, and not need to actually this is not a theoretical question, just for to see the values, the ranges. Okay, then after this maximum degree of curve, elements of a circular curve, elements of a circular curve, elements of a circular curve. So or another thing in your this relationship, the important relationship is actually helpful in determining the degree of the curve at any point by measuring the Varsine either in centimeters, suppose on a 11.8 meter chord, or inches. Inches are not important for your calculations. Normally 62 feet are used if 11.8 meter chord is if it is in meter, suppose in FPS unit is given, then 62 feet chord should be taken. So the curve can be of as many degrees as there are centimeters or inches of the Varsine of the chord length. And after that, the elements of circular curve. Elements of circular curve, in elements of circular curve, you can see the some elements of circular curve. You can see in the figure, suppose AO and BO are two tangents of a circular curve. Normally actual circular curve is, this is the actual circular curve. Okay, this is the actual figure through which we can understand the every elements. I am coming this figure. Before that, you can see the in figure AO and BO are two tangents of a circular curve which meet or intersect at a point O, called the point of intersection or apex. T1 and T2 are the points where the curve touches the tangents called tangent points. Okay, OT1 actually, OT1 and OT2, OT1 and OT2 are the tangent lengths of the curve and are equal in the case of simple curve. This OT1 value and OT2 value is the same length of the curve and are equal in the case of simple curve. T1, T2 is the chord. This T1, T2, this length is the chord, and EF is the versine, same as the extended length. Okay, T1, T2 is our chord length, and EF is the versine of the curve. The angle AOB, formed between the tangents AO and OB. AO and OB, this angle AOB is called the angle of intersection. Okay, the angle of intersection should be less than 1. Okay, should be the angle should be less than 1, and the angle BO, BO1, okay, is the angle of deflection, and this angle should be greater than less than phi. So these are the not less than, these are the angle. Okay, these are the angle sign. This is the angle 1 and this is the angle phi. The angle BO1 is the angle of deflection. This sign is given wrong. Actually, this is the angle sign. These are the angles. Angle 1 and this is angle phi. Okay, and the angle BO1 is the angle of deflection. This is the deflection angle and this is the intersection angle. The following are the same of the important relationship between these elements. Angle 1 plus angle phi equals to 180 degree, and tangent length OT1 equals to OT2 should be R tan phi by 2. R tan phi by 2, where we can get this value from this figure. If we see, we can prove the OT1 equals to OT2 should be R tan phi by 2. Okay, R tan phi by 2. R tan phi by 2. T1, T2. T1, T2 is the length of the long chord, this length, and it should be 2R sine phi by 2. Okay, and the length of the curve, should be 2 pi R by 360, the formula of the degree of curve, into phi value. Okay, this phi value. So length of the curve should be pi R phi by 180. That is the length of the curve, and from this figure we can prove all these things. All these R tan phi by 2, T1, T2, 2R sin phi by 2, length of the curve is 2 pi R by 360 into phi, or simply pi R phi by 180. All these things we can prove easily from this figure, and this is the points are defined with A, B, T1, T2, E, F, the angle phi, angle 1, intersection angle, deflection angle, O and O1. These things are defined by this figure, but actual we can prove this figure. This figure is very easy to find out all the values, the T1, T2 values, or chord length values, length of the curve values. All the values can find out this figure. You can see when I will give you the PDF you can easily find out these values. After that, super elevation. We have super elevation, but there is some setting out a circular curve or curve setting out curve. In survey you have seen the practical setting out curve. Setting out curve is not important for theory questions or even for any questions in your exams. Any exams, setting out of curve is not important, but there is one thing, that is setting out of curve, which is actually performed in our lab. Okay, now the super elevation. As you know, the super elevation, already you have idea what is super elevation in your highway engineering, but some terms are used under super elevation in railway engineering. The actual this term you should know, and the following terms are frequently used in the design of horizontal curves, like super elevation or cant. The cant, already in highway also this cant name is already introduced. Instead of super elevation we can say cant also. Okay, cant is very popular somewhere instead of super elevation, or you may get questions in your exams instead of super elevation, what is cant, what is the cant value, or numerical questions where the word may use the cant instead of super elevation. So the following terms are which are frequently used for design of horizontal curves, that is super elevation or cant: equilibrium speed, maximum permissible speed, cant deficiency, cant excess. The super elevation or cant, normally again I should tell the definition, that it is the difference in height between outer and the inner rail on a curve. It is provided by gradually raising the outer rail above the level of the inner rail, and the inner rail, also known as the gradient rail, is taken as the reference rail and is normally maintained at its original level. The main functions of super elevation are to ensure a better distribution of load on both rails, outer and inner rails, to reduce the wear and tear of the rails and rolling stock, to neutralize the effect of lateral forces, to provide comfort to passengers. These are the functions of super elevation. Next, equilibrium speed. When the speed of a vehicle negotiating a curved track is such that the resultant force of the weight of the vehicle and radial acceleration on the curved section due to weight of the vehicle, that is our rail, bogie, engine, due to the weight of this engine, locomotive, bogie, whichever, there is one resultant force. Resultant force are normally generated, and on curved section, in case in highway also, there is some acceleration or radial acceleration, because acceleration is the vector quantity, speed is the scalar quantity. So if speed is scalar quantity, so then your direction is totally is not there if speed is there, because speed is the scalar quantity. But on curved section you have to rotate throughout the curve, you have to move your vehicle, or you need to move your vehicle along the curve. So there should be direction, and when direction is present, acceleration should be there. Okay, acceleration is the vector quantity because direction is there. Normally the velocity over the time, that is acceleration. Okay, so when the weight of the vehicle, resultant force of the weight of the vehicle and of radial acceleration is perpendicular to the plane of the rays. So the resultant, normally in the front side of the bogie or engine, resultant direction of the force, straight direction, and your radial acceleration, okay, perpendicular to the plane of the rails, the vehicle is not subjected to any unbalanced radial acceleration and is said to be an equilibrium. Okay, when these difference between two forces, this resultant force due to weight of the vehicle and the acceleration, radial acceleration, these two direction at the same place, suppose horizontal plane, at horizontal plane, if the difference of these two direction is 90 degree or both are perpendicular, then your vehicle is balanced, in a balanced position, or there is no chance for accident. Okay, so and we can say this is said to be in equilibrium. This particular speed is called the equilibrium speed, and this maintained speed on the curved section due to adjust this phenomena, to adjust this equation properly, to balance the vehicle. This is called equilibrium speed, and the equilibrium speed as such is the speed at which the effect of the centrifugal force is completely balanced by the current provided. Providing super elevation, the effect of the centrifugal force is completely balanced. Okay, so speed which is maintained to satisfies this equation, that is actually equilibrium speed, and also due to providing the super elevation or current, the centrifugal force also is completely balanced in that curved section. Okay, maximum details of the equilibrium speed will come. Okay, the maximum permissible speed, this is the highest speed permitted to a train on a curve, taking into consideration the radius of curvature, actual current deficiency, current excess, and length of transition. Normally transition curve, you know where it is provided, between circular and straight curve it is provided. When our highway introducing a circular curve, at that position, straight line and that circular position, between two these positions, straight portion and circular position, one curve is provided, that is transition curve, we seen in highway engineering. Okay, so transition curve is between circular and straight position, straight component of the highway or anywhere, suppose in railway also. This transition curve actually the consideration of the radius of curvature, actual current deficiency, current excess, and the length of transition curve, these things are related for maximum permissible speed of the track. On curves, actually our engine capacity is high. Normally in Indian Railway our engine can run with high speed, but due to track condition, due to road condition, we are ruled, or we have provided some limitation for particular road. But some cases some trains are only they are allowed to go with high speed with special consideration, like Rajdhani can go with high speed anywhere, but for that purpose, for that time, the Indian Railway employees are taken high precautions, high observations, all those things are related during traveling the when movement of the Rajdhani is happen in our railway track. But normal cases for all the trains except Rajdhani, but all the trains, the some speeds are provided, some rules are provided for speed. However, your engine is engine's capacity is high, no matter, but you will go as per your track condition, and it is provided by the railway engineer which is speed is applicable for that particular track, and you have to maintain during your travel or when your engine will move on this track. You should maintain this speed, this ruling speed. So for that purpose this maximum permissible speed is coming, and for this maximum permissible speed lots of factors are involved: radius of curvature, actual current or actual super elevation, current deficiency, we are coming what is current deficiency, current excess, and length of transition curve. On curves where the maximum permissible speed is less than the maximum sectional speed of the section of the line, permanent speed transition restriction becomes necessary. Next is current deficiency. Current deficiency, it occurs when a train travels around a curve at a speed higher than the equilibrium speed. It is the difference between the theoretical current required for such high speeds and the actual current provided. Again I am repeating, it occurs when the train travels around a curve at a speed higher than the equilibrium speed. It is the difference between the theoretical current required for the such high speeds and the actual current provided. Okay. Current excess, it occurs when the train travels around a curve at a speed lower than the equilibrium speed. It is the difference between the actual current provided and the theoretical current required for such a low speed. This is the current deficiency and current excess. Actual needed and which is provided. Same thing for current excess. Where provided less, that is current deficiency, and where provided high, the current, that is current excess. Current gradient and current deficiency gradient. It occurs when a train travels around a curve at a speed, current gradient and current deficiency gradient. This indicate the increase or decrease in the current or the deficiency of current in a given length of a transition. Okay, and a gradient of suppose 1 in 1000 means that a current or increasing portion or super elevation or a deficiency decreasing of current of 1 millimeter is attained or lost in every 1000 mm of transition length. That is current gradient and current deficiency gradient. Another is rate of change of current or current deficiency. This is the rate at which current deficiency increases while passing over the transition curve. Example, a rate of 35 mm per second means that a vehicle will experience a change in current or a current deficiency of 35 mm in each second of travel over the transition when traveling at the maximum permissible speed. So train with its maximum permissible speed, the train will feel the current experience a change in current or current deficiency of 35 mm in each second of travel over the transition. This is the feeling of, or this is the value, suppose as an example 35 mm, which the train will feel in each second on the transition part, that is the current is increasing or current is decreasing, and this is actual provided, that is suppose 1 mm is attained or lost in every 1000 meter of transition length. This is the current gradient, current deficiency gradient, and this is the rate is involved with second or time. Next is centrifugal force on curved track. A vehicle Same things like in horizontal highway engineering. A vehicle has a tendency to travel in a straight direction which is tangential to the car even when moves on a circular curve. As a result, the vehicle is subject to a constant radial acceleration, and this radial acceleration is v square by r. Okay, and the where v is the velocity meters per second, r is the radius of car in meter or meters. This radial acceleration provides a centrifugal force which acts in radial direction away from the center. The value of centrifugal force is given by the formula. This is the actual figure through which we can understand. This is the centrifugal force acting in the outer direction of the vehicle, denoted by F. So this force equals to mass into acceleration. Okay. Force is equals to mass into acceleration. Mass is the m into acceleration is the v square by r. Mass should be the weight by g. Weight, w is the weight, g is the acceleration. Gravity of g is the acceleration due to gravity, and this v square by r. Now, where F is the centrifugal force in tons, W is the weight of the vehicle in tons, V is the speed meter per second, and the G is the acceleration due to gravity, and R is the radius of the car in meters. So, to counteract the effect of the centrifugal force, the outer rail of the car is elevated with respect to the inner rail by an amount equal to the super elevation. Okay, this is actually our super elevation. The outer rail is elevated with reference to the inner rail, and a state of equilibrium is reached when both the wheels exert equal pressure on the rails and the super elevation is enough to bring the resultant of the centrifugal force, and the force exerted by the weight of the vehicle is right angles to the plane of the top surface of the rails. In this state of equilibrium, the difference of the heights of the outer and inner rails on the curve is known as equilibrium super elevation. Okay, this is the actual equilibrium super elevation. To counteract the effect of the centrifugal force, the outer rail of the curve is elevated with respect to the inner rail by an amount equal to the super elevation. A state of equilibrium is reached when both the wheels exert equal pressure on the rails and the super elevation is enough to bring resultant to the centrifugal force and the force exerted by the weight of the vehicle at right angles to the plane of the top surface of the rails. In the state of equilibrium, the difference of the height of the outer and inner rails of the curve is known as equilibrium super elevation. So, equilibrium super elevation can be defined tan theta. Tan theta is the super elevation by gauge. Okay, super elevation is denoted by small e, gauge is capital G. Also, tan theta is the centrifugal force by weight. F, centrifugal is the F, capital F, weight is the W. And from these equations, E by G equals to F by W. E is the super elevation. So, super elevation equals to F into the G by W. Gauge by weight of the vehicle or weight of the engine, weight of the bogie, whatever. Super elevation E equals to W. F can be written as W by G because F is mass into acceleration. So W by G is the mass into acceleration is the V square by R into G by W. So the equations becomes now E equals to G V square by GR, or E equals to, if we need in meter, we can put in kilometer and we can get in meter. So GV square by 127 R equals to GV square by 127 R. Okay. Now E equals to GV square by 127 by R, 127 R, where E is the super elevation in millimeters, V is the speed in kilometer per hour, R is the radius of curve in meter, and G is the dynamic gauge in millimeters. This term is new, will come. What is dynamic gauge? Which is equal to the sum of gauge and the width of rail head in millimeters. Sum of gauge and the width of the rail head in millimeters. This is equal to 1750. You should keep in your mind this value. This value is important for numerical. The G value for this equation to find out the super elevation. G value is 1750 for broad gauge and 1058 mm for meter gauge. Okay, you cannot put the what is the value 1670 value for G value. In this case, the G value should be 1750 for broad gauge and 1058. You cannot put the simply 1000. You have to put 1058 this G value for meter gauge. And the amount of super elevation to be provided is calculated using following formula: E equals to GB square by 127 R E equals to 13.7 V square by R for broad gauge, E equals to 8.33 V square by R for meter gauge. Here E is the super elevation in millimeter, V is the speed in kilometer per hour, G is the dynamic gauge, that is 1750 for broad gauge, 1058 for meter gauge tracks. This is important value. You should. And R is the radius of the curve in meters. Okay. Okay. This is all today's class. Any question? Wait, I am taking attendance. Thank you. Thank you. You can leave. Thank you, sir.